Planets known as gas giants are significantly dissimilar to our own. We already know something about their size and makeup from the term gas giants. In contrast to terrestrial planets, which are predominantly made of rocky material, gas giants are primarily made of gases like hydrogen and helium. They do include a small amount of rocky material, although this is often located in the planet's core. Let's examine the solar system. The asteroid belt can be viewed as the boundary between terrestrial and gas giant worlds. Mercury, Venus, Earth, and Mars are the first 4 terrestrial planets that are visible from the Sun. In order of proximity to the Sun, the 4 gas giants are Jupiter, Saturn, Uranus, and Neptune. We can't walk on these planets like we can on Earth since they are just giant gas worlds. Giant planets and Jovian planets are other terms we might use to refer to gas giants. The word Jovian comes from Jupiter, hence the other 3 planets must be related to it. Uranus and Neptune were found to have different compositions, despite the fact that they are still frequently referred to as gas giants. Different types of elements and compounds make up planets. These planetary components were divided into 3 categories by scientists for easy identification: silicate and metallic rocks. Hydrogen and helium are gases. Water, methane, and nitrate ice. Because of the significant amounts of silicates and metals present, the terrestrial planets, including the Earth, are also known as rocky planets. More than 90% of Jupiter and Saturn's mass is made up of hydrogen and helium. They most likely have a layer of liquid metallic hydrogen inside and an exterior layer of molecular hydrogen outside. Only 20% of Uranus and Neptune's mass is made up of hydrogen and helium. The majority of these 2 outer planets are made of ices. Due to this compositional discovery, Uranus and Neptune are now more appropriately referred to as ice giants. Uranus and Neptune, along with Jupiter and Saturn, are still referred to as gas giants, despite the fact that ice giants have already been given their own classification. These gas giants' cores are assumed to be made of stony or metallic material. Have you heard? Some people refer to Jupiter as a failed star. This is due to the fact that it is composed of hydrogen and helium, just like our Sun and other stars. However, it lacks the mass necessary to produce energy and develop into a star. The largest planet in our solar system, Jupiter, is still quite small in comparison to the size of stars. It is not enough big to initiate thermonuclear fusion at its core. In order to initiate this reaction and hence produce energy, Jupiter actually needs to have at least 80 times its current mass. Despite the fact that gas giants have been there for billions of years, we have never yet witnessed one forming. However, through theories and the use of computer simulations, we may gain a general picture of how they got started. With the creation of the solar nebula 4.6 billion years ago, everything began. This cloud is made up of the same gas and dust that created the Sun. The remaining nebula, which was not utilized in its development, formed an accretion disk as it whirled around the Sun. As time went on, the dust grains on the disk grew larger and larger balls of dust. Planetesimals were created when these balls gently collided with one another. These kilometer-sized bodies became larger when they were struck by more collisions, becoming protoplanets. For perhaps 10 to 100 million years, these protoplanets circled our Sun. Out of chaos, order. The 8th planets were produced by gravitational forces and additional collisions. The formation of the gas giants resembled that of the terrestrial planets. The gas clouds that surround a nascent star, however, only last for a few million years. As a result, these solid planets that will eventually develop into gas giants must rapidly grow larger in order to catch the gas while it is still surrounding the Sun. The Sun was formed by drawing the majority of the material from the nebula. Most of the gases from the closer terrestrial planets were swept away by the powerful stellar wind. The gases of the gas giants were not stripped off by this constant outflow from the Sun since they are considerably further away. Although the origins of the cosmos are still mostly unknown, these theories can shed some light on the matter. Planets outside the solar system are known as extrasolar planets or exoplanets. They orbit various stars and are of different sizes. Some of them are around the size of the terrestrial planets, while others are much larger than Jupiter. Exoplanets are divided into groups by scientists based on the planets in our solar system. We can then obtain a sense of how they stack up against the more well-known worlds that orbit the Sun. That does not imply, however, that these planets are comparable. The planets that orbit each star are distinctive in their own right. Have you heard? It is known that certain exoplanets orbit two stars simultaneously. Circumbinary planets is the name given to them. Unique objects that are not connected to any planetary system are rogue planets. These lifeless worlds are just drifting across space. A gas giant, Neptune-like, super-Earth, or terrestrial exoplanet can be identified. Gas giants are about the size of Jupiter and Saturn. Super-Jupiters are celestial bodies that are more massive than Jupiter. Hot Jupiters are the name for these sweltering planets. The size of Neptune-like planets is comparable to that of Uranus. They are thought to have rocky cores and hydrogen-helium atmospheres in common. The term hot Neptunes refers to several of these exoplanets, Hoptunes. Mini Neptunes are planets that are larger than Earth but smaller than Neptune in terms of size. Terrestrial worlds known as super-Earths are at least twice as large as Earth yet are lighter than Neptune. While some of these worlds might have atmospheres, others might not. Terrestrial planets are also silicate, carbon, water, or rock-based worlds. They are comparable in size to Earth, if not smaller. A recently released catalog indicates an amazing diversity of potential exoplanets that TESS, the Transiting Exoplanet Survey satellite, may have discovered. For gas giants are already known to orbit the Sun. It's interesting to note that there are a lot more of them outside of our solar system. We don't know what these extrasolar planets look like because they are so far away. To comprehend these gas giants better, a classification scheme was developed. It was put forth in the Steady Albedo and Reflection Spectra of Extrasolar Giant Planets by David Sudarsky and colleagues. Based on their characteristics and external appearance, there are 5 different types of gas giants. Class 1, Clouds of Nitrate. Ammonia clouds predominantly make up the gas giants in this class. They are thought to exist at temperatures lower than 150 K, or roughly 120 degrees Celsius or 190 degrees Fahrenheit. These frigid zones are often found where they belong, on the periphery of the planetary system. It might also imply that the star is extremely cold and faint. In this system, class-eyed gas giants include both Jupiter and Saturn. Upsilon Andromedae E, 47 Ursae Majoris C, and 55 Cancri D are examples of potential Class I exoplanets. Class 2, Clouds over Water. Temperatures in Class 2 gas giants hover around 250 K, around 23 degrees Celsius, 10 degrees Fahrenheit. Since these are warmer, water vapor rather than ammonia makes up the clouds. Given that they are coated in aqueous clouds, these planets would have a greater albedo. Ursae Majoris B, HD 45364C, and Gliese 876b are a few potential Class 2 gas giants. Category 3, No Clouds. Class 3 gas giants do not produce clouds because they lack the ingredients required to do so. Between 350 K, 80 degrees Celsius, 170 degrees Fahrenheit, and 800 K, 530 degrees Celsius, 980 degrees Fahrenheit, these planets are located. They would resemble the blue worlds of Uranus and Neptune and are thought to be situated in the interiors of their planetary systems. Metals in Class 4, Alkali. Giants in Classes 4 and V are referred to as hot Jupiters. Class 4 planets have surface temperatures more than 900 K, 627 degrees Celsius, 1160 degrees Fahrenheit. Carbon monoxide replaces methane as the main carbon-carrying molecule in the atmosphere. Although it is projected that these planets would have relatively low albedos, they are becoming increasingly abundant in alkali metals such as sodium and potassium. Silicate clouds, Class V. Class V gas giants can have temperatures above 1400 K, 1100 degrees Celsius, 2100 degrees Fahrenheit, or they can be cooler and have a gravity that is less than Jupiter. These planets are thought to have iron and silicate cloud decks in their atmospheres. This is all for today. Don't forget to subscribe and click the bell icon for more videos. Stay tuned with AWZ.